יכול להיות. אבל איפה טעיתי בספירה?
אולי אני טעיתי. זה קרה
So,
תורת ההצגות,
last time we started discussing finite index subgroups, the restriction of harmonic functions to finite index subgroup. So remember, I'm reminding you what the theorem was. The theorem was that if we have a finite index subgroup, then the space of polynomially growing harmonic functions is isomorphic. Where on the subgroup, we take the hitting measure. So the hitting measure is just observing the random walk at the successive times that it returns to the subgroup. And so finding what this is, okay, so it's just the probability to hit X at the return time. And another.
Which of these objects is related to mu?
Yeah. What?
You have to have some dependency on mu, right? So which
yeah, so mu h comes from mu. This is a random mu random walk.
Okay.
So
did we state it for K or for infinity or for
state it for any K.
For any K?
Including K equals 0.
Including K 0? 0 is
bounded.
It's not finite.
K is the rate of polynomial growth. If your rate is 0, then you're bounded.
And finitely supported is
finitely supported. These are functions. K is for the functions. This is the space of functions which grow at most like a polynomial of degree K.
Okay.
The condition that you're thinking about is on mu.
Okay.
So what we did it is for
Let's see.
Symmetric adapted with exponential moment. Okay, it's true that you can do it for smaller things, but you have to be careful. First of all, this is not defined. If this is not defined, if mu doesn't have kth moment, things don't converge, and so you need to be careful. But
if you take mu to have like a k moment, it's only true for
no, it
numbers less than k.
No, it's actually true for. Yeah, so if you take mu to the kth moment, it's still a little bit true, but you need to work harder to prove it. Okay, so it's not the most general case. Okay, so this was a situation, and one more piece of information that you should know, or you should remember, is that this thing has an exponential tail. So this starting time has an exponential tail because the quotient, because there are only finitely many cosets. Okay, the quotient is around the walk.
Wasn't there a delta?
Yeah, I could have seen. Doesn't matter. You want a delta?
No, I didn't know if there were also a delta and a C, I think.
There was a C outside, but I can swallow it into the delta. Okay. Doesn't really matter. Okay. All you need to remember is that this has an exponential tail. It has an exponential tail, that means it has all moments. Okay, that's easy, right? So good. And what we proved is okay. So what we did is that the proof. We're in the middle of the proof. We proved that the restriction map is the isomorphism, or we want to prove that this is the isomorphism, right? And so for this, we need to show that the isomorphism, that the restriction is surjective and injective, okay? And surjectivity
is actually immediate for restriction. You just want to show that it's well defined. So we show that the restriction is harmonic.
Showed it?
No, to show that surjectivity is not by restriction, because
No, to show injectivity.
you need to show that you can get any harmonic function on H by restricting some harmonic function on G. So there needs to be a way of extending harmonic functions.
See, this one would be.
And here's the one, last time I'm just reminding you, so surjective, right, comes from the fact that we can define, so if we have something which is in H, then we can define a function on G, which is just the expected, you start from X and you stop at the first return time. Okay? And it has to be this because of the optional stopping theorem. If there would be a harmonic function, if it would be true, we're trying to prove something. If it's true, this has to be satisfied. So it's a good way to define it. Always look, I'm trying to prove something. If it was true, what would happen? Oh, this would happen. This forces my hand. I can't make any other decision.
Then the mean value theorem.
This is the optional stopping theorem. I'm just saying that if this was a harmonic function, okay, whose restriction was equal to f tilde, then you would then it satisfies the optional stopping theorem, and you can replace f with f tilde here because this is always in H. By definition. Okay, and what we proved is that this is the same thing as this. Okay. The proof of this goes by splitting into two cases: if x is in H and if x is not in H. Okay, and it uses the fact that f tilde is an is a mu H harmonic function. Right? If you want these to be equal, you need the f tilde, because when x is in H, this is after one step and this is at 0 steps. So you have to say that 1 step and 0 steps, the expectations are the same, and this comes from the harmonicity. Okay, so this was the whole idea of this thing. You have to show that everything is well defined and converges appropriately. But once you show this equality, then the fact that f is harmonic is immediate, and of course its restriction to H is exactly f tilde. Okay, so this was the surjectivity, and now we move to the injectivity.
How is that the optional stopping time theorem?
I'm just saying, if f was harmonic, then by the optional stopping theorem, we would have to satisfy this. F of x is equal to the expectation starting at x at a stopping point of the random walk of the stopping. Because f of xt is a martingale.
Oh, f of x
Okay.
is a martingale, so
F is harmonic,
the
f of xt is a martingale, and so the expectation at the stopping time is equal to the expectation at 0.
this is the expectation of 0.
Well, at 0, you're at x. Okay? But then when this, putting a tilde here or not, is the same thing, because you're assuming that f is a function whose restriction to f tilde. I'm just saying that's not the proof. I'm saying, how do I come up with the proof? I come up with it by thinking, suppose I had such an f that what? That it's harmonic and that its restriction to H is exactly f tilde.
This idea I get, it just didn't know how it relates to optional stopping time.
Okay, and now we have to do injectivity. So what does injectivity mean? It means that if I have a function, so assume that f is a function in the domain of the map such that its restriction to H is identically 0, right? This is what we want, right? Injectivity of a linear map to just show that the kernel is...
Even like the same thing?
Yes, well, 1 second. Okay. So we assume that f is here and that it's that it's in the kernel, right? So it's the restriction takes it to the 0 function, okay? And we want to prove that f is actually itself 0 on all of G. Then what we do is we look at f of xt, okay? We can do it minimum with th, right?
This is you random walk.
Yeah, xt is always the new random walk. Okay, already over there. Okay, so if I look at this guy and I define this to be MT, right? Then I claim that MT is uniformly integrable. Let's check that. So MT, okay, now you have to remember F is from HFK, meaning it grows like a polynomial of degree K. So there is some constant such that this grows at most like time well, so f grows at most like xt plus 1, all of this to the power of k. The plus 1 is just so that it's not 0, right? Okay, this is the condition of f being in h of k. And this thing, well, okay, so this we showed, or is already has finite expectation. By the way, remember that uniform integrability is easier than it's easier to prove if you just prove a bigger moment. Let's put a 2 here. Okay. Right. If I just saw that the supremum over these things is bounded, then I have uniform integrability. Right. So
In 2K.
yeah, then I need 2k. No, I'm sorry. I just needed to show that the supremum over the MTs is bounded, right? That's all I need to show. Okay. And so this is less than or equal to this. Okay. So I need to show, I need to bound the expectation of this guy. Right? If I just show that the expectation of MT is uniformly bounded in T, then it's uniformly integrable. That's a stronger statement than uniformly integrable, right? Because for the uniform integrable, you also put a little indicator. No, sorry. You put the indicator, you need to go to 0. Yeah, so we do need 1 plus epsilon or 2. I'm going to do 2. It's not going to be important. You see, this is part of the issue where I'm going to use the exponential tail. It makes everything my life much easier. Okay? So exponential tail of 2 things. I'm going to use the exponential tail of TH. I'm going to use the exponential tail of mu, which is what makes my life easy. TH is always effective exponential. Okay? So the expectation of MT squared, I could have taken 1 plus epsilon. It's unimportant, but I need anything slightly stronger than 1 for the uniform integrability is less than or equal to this, which is less than or equal to the expectation of this. And now we use the usual trick by splitting into, let's go up here. This is less than or equal to, I have my constant, I can sum over all possible t's, right? And then I can look at the indicator that th is t, right? So, okay, let's actually try a different thing. So we split it into 2 events, one where th is bigger than t, one where th is smaller than t. And yeah, okay. So this is less than or equal to the constant times the expectation of what? Of xth plus 1 to the k, where th is less than or equal to t, right? This is one event, okay? And then I can get rid of this, this guy.
I don't know if it's important, but you need 2K.
Well, yeah. Yeah, actually, I'm going to do it anyway. So we sum overall. I can't do t. T is in, and then we look at the expectation of what I have here. On the indicator, the th is in, and then I can replace this th with n. Right? So this is just I just split this up. Now I'm going to use the Cauchy-Schwarz. Use the fact that t has an exponential. Okay, I'm going to do a Cauchy-Schwarz. First of all, I want you to notice that when n is smaller than t, then I get an n here. Okay, and when n is bigger than t, then I just get a t. Right? Yeah, so now we do c sum square root of expectation of xt minimum n plus 1 for k, right? Times the probability that th is equal to n. Right? So this goes to Schwartz. And this thing I can always bound because, yeah. So, well, I want to put this, I can pull the square root out also because of the sums. Let's be careful here. Yeah, so this expectation is always bounded. Okay. Okay, so let's split this into two sums. Sum n is at most t. Then I have square root of the expectation of xn plus 1 2k. Okay, this is always bounded by starting. Okay, plus c times the sum over n greater than t. When n is greater than t, this is just t, so this is a constant thing that comes out. Here I threw away the probability, just bounded it by 1. Here, this xt plus 1 to the 4k comes out. Okay? And what do I have? Sum over n greater than t, this is the probability. I have a okay. I need to keep it in this. Yeah, okay. So let me write. So this is the sum over n greater than t of this another constant e to the minus delta n, because the probability that I'm equal n is less than at least n. Okay, and then I have to put a square root on for 1 over 2. Okay, the reason I need to do this is because it's a sum of square roots. I have the square root here, which bugs me a bit. So I couldn't just get the probability of t bigger than. Okay, now this is basically just some exponentially small in t. Okay, this is exponentially small in t. This is polynomial in t. Okay, we need to prove this. If mu is in SA infinity, then this thing grows like t to the 4k. Okay, so this is going to be an exercise. This thing grows like t to the, this thing grows, well, this is fine. This thing grows like n to the 2k, then the square root is n to the 4. This isn't good, right? This depends on t. Okay. Sorry. So we can't split it into two sums. Want to bound it? Okay. Again,
What are we trying to do?
I want to give a uniform bound on this. Without doesn't depend on t. Okay. So this is constant. I have the sum going from 0 to infinity. Okay.
We want to say that f is equal to 0, right?
I want to show, okay, I want to show that f is uniformly integrable, that mt is uniformly integrable. When mt is uniformly integrable, I can use the optional stopping theorem. Once I use the optional stopping theorem, then I get that f is 0, right?
We can't use that one, or maybe I missed something. We know that the equation from the subjectivity.
Sorry, what?
The equation from the subjectivity, can't we use it instead of the power, like that one on the left? Not the way.
Projective.
Yeah. So that one equal the expectation starting at f of f without the very.
Yes, I want to use the optional stopping theorem, but then I need this martingale to be uniformly integrable. That's the idea. That's what I'm trying to show. So maybe yeah.
Need to use it also for such subjectivity or no, or no.
Okay, let's go back here. We're going to have to prove this separately. What I want to prove is that what actually is going to go, what's going to happen here? I want to give a bound on this thing. Okay, so I want to show that this is basically bounded by this minimum to the power 2k. Okay, and the reason is that, you know, I couldn't have any large jumps, right? The largest jump is something because mu has an exponential tail. Okay, so let's bound this. All I need is I want a uniform bound in t. And the reason I can get a uniform bound in t is that this should be smaller than roughly this time to the power 2k, maybe with some constant. But that time is the minimum between t and th, so that's definitely smaller than the 2k moment of th, which is a finite number independent of t. That's the bound I want to give. Okay, this is what I was trying to do here. Let's give a bound. So what we want is we want the maximal jump up to time. Maximal jump. This is written as just different jumps, and we want the maximal jump up to time t minimum th. Okay, so we write xt is u1 ut, right? And these are independent. Okay. Now, so what is this? So this is always less than or equal to. We have the C, we have the expectation, and inside we have the expectation, we have the sum. Okay, sorry. So we have the maximum, J is at most T minimum TH, right? Of UJ, okay? This times T minimum TH, right? This bounds this guy, right? But the triangle inequality. All of this plus 1 to the power 2k. Okay? So I need to give some bound on this guy. Okay? I need to give some bound on this maximum. Now, for this maximum to be big, right? For this maximum to be big, one of them had to be big, right? Means that one of them had to be big. But how big is one of them be? They have exponential tails, all of them, because of mu. These are just I d mu. Probability that one of them is too big can be made as small as I want. Okay, and I just get another factor of t minimum th, just for the union bound, right? So probability at the maximum is bigger than some lambda. Okay, this will play around with lambda later. This is less than or equal to, there exists one of them that's bigger than lambda, right? But they have exponential tails. Okay, so this is less than or equal to t minimum yeah, it's random time. Okay. Yeah, it's a random time. This starts to become formally doing. Okay, so let's call this random variable without the 2k, let's call this y. Just some number, okay? Some random number. Now, what is the probability that y is greater than lambda? Probability that y is greater than lambda is, what does this mean? It means that either I had a big jump or I waited for a long time. Okay, or both. Okay, so this is less than or equal to, or put it the other way, if this time is less than or equal to lambda, okay, and no jump up to this time was bigger than lambda, or square root lambda, okay, we could do square root lambdas, right? So if this is less than square root lambda and this is less than square root lambda, then their product is less than or equal to lambda, okay? So for this to be bigger than lambda, this means that either this is bigger than lambda, okay, or this is less than or equal to lambda, and one of the jumps up to lambda was big, right? We want square root lambda, sorry, because it's a product of two things. Lambda is some big number that I fix. Okay, there exists a j such that uj is bigger than square root lambda. Okay, I could play around with any numbers, we can optimize, but you won't need to. Okay, again, if this number is bigger than lambda, one of them has to be bigger than square root lambda, which means that either this is bigger than square root lambda, or it's smaller than square root lambda, and then this is not too many j's, and one of those j's has to be, give me a big jump. So it has to be, okay, so this is just a union bound. Okay, now, this is less than or equal to, for this to be bigger than square root lambda, well, this has an exponential, I mean, if this is big, then t is big, so it's just an exponential tail, right? So this is less than or equal to some constant, e to the minus delta square root lambda, right? Because this guy has to be bigger than square root lambda, the minimum, okay? Plus, this is, I have square root lambda union over them, and then I have the probability that some mu is bigger than square root lambda, right? But that also has an exponential tail, maybe with a different exponent and a different constant, but you know, up to making this big and this delta small, it's the same constants, right? So it's e to the minus delta square root lambda as well, and here I have a factor of square root. Okay, and I disregard even this plus one. Okay. So this bounds the tail of y, but then you see that this is exponentially decaying in square root lambda or whatever. Okay, so the expectation, so this implies that the expectation of y to the 2k for any k is finite. That's all. That's all I need. Right? Okay. This just shows, right? Because I mean, this is to sum over lambda to the power 1 over 2k, these things are summable. It decays much faster than this.
Okay. First inequalities.
This inequality?
Yes.
Again, the event that this product, okay, the event that this plus 1 is bigger than lambda is implies that it's just the product is bigger than lambda. Okay? The event that the product is bigger than lambda means that one of them was bigger than square root lambda. But in fact, it means that either this product was bigger than square root lambda, or this was smaller than square root lambda, and this was bigger than square root lambda. Now, when this is smaller than square root lambda, then this maximum is definitely less than the maximum all the way up to square root lambda. So I have to have one that was before square root lambda that had to be a big jump. Otherwise, the maximum would be smaller. Okay? So this uniformly bounds this thing, and so NT, yeah, it took much more time than I wanted it to take, but anyway. Well, it's because when you get used to these things, they're so immediate, you don't think about the actual proof. So So MT, so FXT minimum TH, this is uniformly integrable martingale, right? And so Fx, which is the expectation x of M0, right, is equal to the expectation x MTH, but M at time TH is exactly F of x at time TH. So this is, but this is what? This is an element in H by definition. And we assume that the restriction of F to H is 0. This has to be 0. So this shows that F is identically 0. Okay, this is what you wanted me to do.
Yeah, but so can you explain again why on one side you didn't have to do all this calculation and or we had to show that it's a uniformly integrable and one side we
I didn't use the optional stopping theorem. That's what I was telling Gal before. I didn't use the optional stopping theorem to prove this identity. I said that I come up with the identity with the definition because I know that if I proved that if what I want to prove would be correct, I would have the optional stopping. But when I want to use it, I have to actually prove that it applies.
so here we didn't use it, we just like okay.
I could have told you intuitively this martingale is uniformly integrable, prove it,
No,
and then we have the optional stopping theorem, which is what I actually did in my head when I was preparing this. And then I said, okay, it's obvious that it's a uniformly integrable because we can bound everything because TH has an exponential tail. You see, what I used here is that TH has an exponential tail. This was the important part. The fact that these U's had an exponential tail was less important. Yeah, I could get away with something maybe like a kth moment here or something like that. I couldn't get away with a 2k here, so I couldn't do the Cauchy-Schwarz thing, but or the square there. And so I would have to be much more careful. If I only had a kth moment, I would only be able to work with k here, and I would have to be careful. It would still be okay, but I would have to be careful, and I would have to go to the strictly proper definition of uniform integrable, the indicator that MT is big and all that.
So why did and so that's the second question, why did we choose can you explain again why did we choose the 2?
Because we said that, remember there was this, if the supermoon of T of the expectation of MT to the power 1 plus epsilon for some epsilon, if this is finite, then you get uniformly integrable, right? But you need an epsilon to beat that extra little tail. It's not enough to bound just the supermoon of the.
Yeah, that's
Okay.
Yeah.
Okay, so I was planning on getting to this much earlier, but anyway, okay, so we proved that finite index groups, we can pass freely to finite index subgroup and we don't change anything. We have to move to the new measure, which is the heating measure, but it's the natural measure that we want to talk about. Okay, what I want to do now is I want to start talking about entropy. Okay. So what is entropy? Anybody know what is entropy? Iran, you know what entropy is? Iran is a physicist. He knows what entropy is.
I also know something.
You know something about entropy? So what is entropy?
It's a way to like measure on how much uncertainty a system has or how much information.
Yeah, it's not clear exactly what that is.
I know it has something to do with the logarithm.
What does it mean? How much information is there in the molecules in this room?
I just need to calculate
No, you measure the sun, but what is information?
Yeah, so that's one answer to these questions. Yes, entropy.
But for us, it's more like the computer science definition of it. It's not mathematical. It's Shannon entropy.
Well, okay. So first of all, we just got into a big argument at this conference that I was last week because there was someone there, I won't say any names, this is being recorded, that was insisting on different, Shannon and not that. But actually what happened, so Boltzmann was the first, so first of all, the word entropy was coined by a German physicist whose name I forgot, already in the 19th century. Boltzmann, when he did his seminal work on thermodynamics, he introduced the mathematical definition of entropy, but Boltzmann was also only interested in uniform distributions. Because you can think that, basically if you, the uniform distribution is kind of the limiting distribution of this, the molecules in the room or in a glass or something, right? When it comes to thermal equilibrium. So, all the molecules, right, when you mix the coffee, all the molecules of the milk and the coffee, they are kind of evenly, uniformly spread. But then Gibbs, which is roughly the same time, just a bit after Boltzmann, he built on Boltzmann's work and he understood that, well, if you want to talk about some general distribution, then you can define something else. It kind of seems that Boltzmann already should have understood this. I would bet that Boltzmann understood it. It doesn't appear explicitly in his works, but it appears in Gibbs' work. And Gibbs and Boltzmann died before Shannon was born. So we can't say that Shannon invented entropy. Now, this does not diminish Shannon's contributions to entropy, because Shannon was the one who understood the relevance of this thing to information, and he came up with a definition independently, supposedly von Neumann told him, or somebody, I don't know who told him. How could it be von Neumann? Maybe it was von Neumann, I don't know. Somebody told him that, this has already been done in physics, you should look at thermodynamics. Shannon writes that it's already implicit in works of Boltzmann and Gibbs. And also there was Planck along the way who understood something before Shannon. Planck was before Shannon. So Shannon was in the 50s. This was much later. And he understood the relevance to information theory. And he defined it as a measure of information. Okay? I'll give you a different definition today, a different axiomatic way of coming up with entropy, showing how it pops up. But you should understand that this is a very, very fuzzy object. In terms of philosophizing about it, people can go on forever and still not get anywhere. So you have to be careful with these things.
All definitions are.
For modern physics, the understanding that information is somehow fundamental is very, very important. They like to talk about information. So conservation of information is more fundamental than conservation of energy, of momentum, or things like that. So and what that means, I don't want to get into because I don't know. Okay, and maybe nobody knows, but somehow conservation of information is very, very important. So, and this has to do with entropy, but there are different notions of entropy. When you see the word entropy, it should light up a bell. It's like saying, well, Xn converges to X, and then you have to ask, well, in what sense does it converge to X? So what entropy are you talking about? For example, in ergodic theory, they talk about different entropies, you have subshifts, or whatever. So there are different types of entropy. But the most classical one, indeed, today is Shannon entropy, or what's called Shannon entropy, which was actually Gibbs, and it's very, very useful. Very useful in many things. It comes up in many different seemingly unrelated areas. So there is something in nature that wants to give us entropy. But let me give you a description, okay, of that entropy. So I'm wasting time on this just so that you get some other ideas outside the realm of harmonic functions and walks. So suppose we have this following situation. We're restructuring the Council for Higher Education in Israel. We want our scientists to do proper work. Okay, it's not the mathematicians, the other guys are the scientists. Okay, because they're actually telling us things about the world. And so what are they telling us about the world? Well, we want to give them the ability to use distributions to describe the world, because it's very hard to sometimes say, well, I know exactly what's going to happen next. Why? Because I can't exactly measure the situation. I don't have full knowledge of the system. But many times it's useful, and especially in thermodynamics and things like that, or even in quantum mechanics, it's very useful to use probability distributions to say, well, I can't give you an exact prediction, but I can give you a probability distribution on future states. So if I'm at state I, then the probability I will be at state J in the next time step is Pj, okay? And again, this ties into Markov chains very nicely. Like if you think of Markov chains, physics evolving according to a Markov chain, right? If you know the exact state of the system, then you know the distribution of the next step. So we have this, okay? So we have a certain situation, and we let all of the physicists and biologists and chemists, they all come and they submit their predictions for a law of nature. What is a law of nature? Given the system in a certain state, what is the probability of the probability distribution on the next states? Now, for example, we can play this following game. I have a deck of cards. It has 70 red cards and 30 blue cards. and I'm going to tell you, please predict, you don't know how many cards. Please predict, the law of nature. What happens when I shuffle the deck and pull out a card? What color do you see? That's kind of a law of nature, right? And you can't be completely sure because the shuffling is incomplete information, but you can give a probability distribution, right? So you observe, you observe shuffling and pulling out and you make observations and you do your statistics and you experiment and you come up with a prediction and you submit your prediction. Now, I want to give you money, right? Or I want to give you a reward based on your prediction, okay? I want you to come up with the best prediction, right? I actually want you to give me the probability distribution, which is 70% red, 30% blue. This is what I want you to do. I want to maximize for that. So naive thing, first of all, what I'm going to do is I'm going to promise you, or many people guess this way. I'll just promise, whoever's right, correct, whoever's correct in their prediction. You say, what is going to come out when I pull out the card? If you're right, you get $1. If you're not right, you don't get it. Okay? Now, does this give you incentive to give me the correct distribution? Yes? No. Why? What is the best thing for you to do to win the most money?
Yes.
No.
Pick always red.
Always say red. If I only reward you for your successes, and this is what we do as a society, and this is why we have rabbis and prophets and things like that, right? Because you get only rewarded for successes and you never get penalized for failures. This is the big difference between science and other things. And psychologically, we're built to remember successes. This is something kind of maybe evolutionary programmed into our mind, okay? We forget traumatic experiences of failures and we remember successes. And so this is why people always say, yeah, we just give $1 to whoever succeeds. Look, he succeeded in predicting it 5 times or 7 times out of 10, he succeeded in predicting it. He's a prophet, right? No, I mean, of course he's not a prophet. It depends on the actual distribution. And the fact is he doesn't have any knowledge at all, right? He's just betting on the maximum. And if the probability distribution becomes more complicated, then of course it's much harder to bet on the maximum. So, so we need a different method, okay?
Different method for measuring.
For rewarding or penalizing or somehow, paying money or saying how much do you need to pay for. So what we're going to do, suppose we're going to make you pay money. Okay, you can think of it, we give you money, but you have to pay every time you're wrong. This is just so suppose I make you pay. If you give me a probability distribution, so this is a probability distribution on n states. Okay, suppose there are only n states in the world. Okay, for example, n is equal to 2 if it's blue or red, right? Like if we're discussing a specific law of nature, it has n possibilities, and p is some vector pi, right, which sums up to 1. And suppose I penalize, the penalization is b of p. This is the penalization for guessing or predicting prediction. So a prediction, when you submit your prediction as a scientist, you submit probabilities for everything. Okay? For example, the prophet would choose if n is equal to 2, it's red or blue. The prophet would choose just delta measure on red and 0 on blue, right? This is a probability measure. And we want to incentivize the actual probability measure. Okay, so B of P is the prediction. What did I call here? The real reality, nature, God, whatever you want to call it, reality is Q. So Q is the actual honest to goodness probability measure. In the example of the cards, Q is 70% red. So Q1 is 0.7 and Q2 is 0.3. Okay? So this is reality. Now, what is the expected cost you have to pay? Right? What is the expected amount you're going to be charged? Right? So you give a prediction, we run an experiment, everybody gives in their predictions, we run an experiment, and then your taxes are governed by exactly, how much, what happened, right? So you pay according to what happened, right? We don't know, nobody knows the real thing. So we just look at what happens, and B is the, right, how much you pay for, or maybe I should write, B of alpha. Well, okay. So B of alpha is penalization for well, okay. For PI equals alpha. Okay, if state I came out. So what I do is if state I happened, I charge you the money B of PI, what you predicted to be the probability. Okay? This is the money you have to pay. And so what is the expected?
Where is the I enter the B or?
So it'll be maybe clear when I write this down. So expected payment for prediction P, if you predict some probability measure P, right? What is the expected payment? The expected payment is to go over all the states, the probability that state J came up, which is QJ, and I charge you B of what you predicted. You predicted PJ, I charge you a certain amount of money. Okay? What do you want to do? You want to, of course, minimize your payment, right? You want to minimize your payment. So how should this penalization work? We need some rules about this penalization, right? This is just an abstract way of structuring our payment system. Okay, we structure our payment system in a way that for every real number, we have a function that tells us how much to pay, and everybody pays according to what they predicted and what came out. Okay, and abstractly, the expected payment of somebody who gave a prediction, a list of numbers, which is P, this would be their expected payment.
How can we see that if I get everything correct and I don't pay? Or I don't get.
No, you don't. Getting correct is saying P is equal to Q. So these are the rules. I didn't say what B is yet.
Oh, okay.
I didn't say what B. So the rules are as follows. First of all, we want the expected payment to be minimized for P equals Q, right? We want you to be incentivized not to pay. So to give me the correct thing. Okay. Second, if you're very smart, then you could actually split the next time frame, right, into two steps. You can say, well, I know how, if you're even more sophisticated than what most scientists are, you can actually say, well, I'm going to predict what happens at time t plus a half, and then from t plus a half, I'm going to predict what happens at time t plus 1. So you could go in two stages, and what we would want is that doesn't help you to get any less payment, right? I mean, you should be more accurate, not less accurate, okay? So what we want is that if I'm going to predict two steps, what does that mean? That means that I can predict two numbers, PI, this is a probability distribution already of two numbers, right? Well, so if I want you to predict, two steps in advance, then you're predicting that it will first be I, then be J, right? That's already much richer information about what's going to happen in the next two steps. And of course, you can always predict the next two steps by first predicting one step and then predicting, well, maybe we should do it from right to left. So first predicting what happens next, and then predicting, what happens given J. For every J, you have one step given that J. Okay, right? If you're complete, right? If this is much better than just this, and this is much better than just one step in the future, right? So the scientists who can do this are much better scientists, of course. And we don't want them to be worse off than somebody just guessing, right? So what should this mean? It means that we shouldn't charge more money, right? Or we should charge the same amount of money if you know this than if you know these, right? So
But this is supposed to be the expected payment, right?
yeah, okay, it's not exactly that this is equal to this, but if you know this and you know this, oh, so this should be a product, right? So if you know what the probability is to go to get state I from the current state, to get state J from the current state, and then to get state I given that state J, right? Then of course you know the probability to go to get in the next two steps J then I, which is what this represents, right? So it should be that this number, whatever this function does, it shouldn't change if you do this, right? These should give the same value for the function. But these could be any real numbers, right? I mean, you can always cook up some experiment or some scientific prediction where these numbers are any two real numbers. So this just means that my function takes multiplication, right? Okay, yeah. So, okay, these should be any two real numbers, right? But if we could do it in any two steps, then, I mean, what do I penalize you for guessing this and guessing? Well, I should penalize you for guessing one step and then for guessing another step, right? I mean, it should be the same. So this should be equal to, you know, the probability, the penalization for just saying, I know how to get step J in the next, the prediction in one step, plus the penalization, you know, how much would I penalize you? Now J would be given and how would you predict the probability after state J, right? So what this equality is telling you is that actually B is a function that takes products to sums, and there's only one such function. Well, okay, we need another assumption that B should be continuous, right? I mean, if two people have very, very, very close probabilities, they should be paying basically the same. I mean, right? Should be continuous. That's all I'm assuming, not any Lipschitz continuous. It should be continuous, and so that's another rule, right? So okay, so B is continuous. And also, yeah. Oh, and I said minimizing for people. So what does this mean? So first of all, this second rule plus continuity just tells me that B of X is log X to some base. Okay, so there's a constant here. Okay, and you have freedom to choose that constant. Negative, positive, whatever. So you can think it's penalization or reward, it doesn't really matter. I said minimized, so it's a penalization, but you could change it. Okay? And but what does this mean? This means that the expected payment for a prediction, what is it? It's the sum of Qi log some base, which is coming from the C, right? Log M, let's say, of Pi. Right? That's what we said the expected payment is. Okay? So you see why the log comes up in these things. And by the way, this is a negative number, and I don't want to have you pay me a negative number, so we're going to put a little minus sign. I mean, it just changes the sign, size of M, right? Okay, and then we have freedom to choose M, so let's choose M equals E. Why not? Well, in computer science, they usually choose M equals 2, but we'll choose M equals E. It doesn't really matter, just an multiplication constant. Okay. And here is a exercise for any QP probability distributions and states, sum of QI log PI is always less than or equal to we're doing the right direction. I was confused here. Is always less than or equal to the sum minus the sum of QI log QI. Okay? Did I get it wrong? No, it's the opposite. Exactly.
Yeah.
Proof, how do we prove this?
Convexity. You can do it by convexity.
Yeah, who's
Also,
convex?
Log.
X log. No, log. Just log.
No,
Right.
log is concave.
Minus log.
Minus log.
Minus log is concave.
Well, so what does the okay, so if we bring this to the other side, right, then what we have sum minus QI log or minus log, okay, minus log of PI divided by QI, right? This is the difference between the two things. Okay, and minus log looks like this. So the expectation of minus log
We're using the
is bigger. Yes, it's an inequality. The expectation of minus log is bigger than minus log of the expectation. So this is bigger than, right? Take the average of 2 points, it sits above the function. So it's bigger than than minus log of the expectation. This is an expectation of something because it's sum of QI times something, right? So this is bigger than minus log of the expectation of what's written in here. But this is what? This is okay. This is, by the way, called this object is called this object here. This is called the Kullback-Leibler divergence, and we'll come back to it, of P with respect to Q. And this is not symmetric in P and Q. Because you see it's non-negative. Right? Okay, so we'll come back to this notion. So it's related to entropy. So you see that what you get from all of this kind of thought experiment is that this is a penalization, or right? The penalization is minus log of your number, right? And if you give minus log of your number as a penalization, if you have to pay minus log of PI for outcome I for your prediction, then you're incentivized to give me PI equals QI. It's right. If you give me PI equals QI, you pay nothing, or you pay the minimal amount that you can pay. I can say that we can organize this. So you can pay the minimal amount, And we can reorganize this so that you pay zero if you, or we can give you a reward and you get, the penalization comes off the reward, it doesn't really matter, right? So you're incentivized to give me PI is equal to QI, and any deviation continuously, though, goes away from this penalization. And this is where entropy comes from. Okay? This is one way that entropy comes from. The correct way to measure how much information you're giving me with an incentive to give me the best information. So, one way of interpreting information is that you should be telling me something that I don't know. Okay?
What is the